Okay, discovering the chain rule. The following table shows functions and their derivatives. You want to determine a rule, the chain rule, that would allow you to determine the derivative of those complicated functions and simplify the derivative. So basically, we've given you function, derivative in a not nice form, and we want a nice form of the derivative, right? So where we simplified as best we can. So let's work on, I'll let you, you can do the first one, I'm pretty sure, right? Actually, maybe even the first two. So try the first two. So we can see that you're going to take 4 times 2, obviously you get 8, put that number in front, right? So we're just getting a simplified form of it. It's like, where did that come from? That's the chain rule. We're going to try and discover it.
But you don't want us to expand, right?
No. We never expand, right? Never expand. So the next one, you say, well, okay, what have I got here? I got a 2 in the denominator. I've got this negative root, right? So then we're just going to go with 2x minus 5 over 2 times the root of, right? We change back into radical form. Right, and make sure that your radical signs extend as far as they need to, right? As do your, division bars. The next one we see, hey, you could factor like a 2x out of this, right? So if I factor a 2x out, I'm going to get 2x times negative 3, so that's negative 6x. I'm going to go with the, wait a sec, this negative 4 thing says, hey, that's going to be in a, so we don't have much room here, do we? You have more room on your paper, right? Yeah. Not much room here. All right, let's see what I can do. So, let's just go to a blank. Does this one have more room? Nope. Nothing's got room. Let's see if I can get it there. I don't know. We'll just go down a page. Okay, so what are we looking at? Y prime is equal to 3, negative 3, 2x cubed minus 5x squared to the minus 4. Okay, so let's start off with. So we'll factor 2x out of this, right? That'll give me negative 6x. And what's left here? Well, we factored a 2x out of there, so that's 3x minus 5. And this has a negative exponent, so it needs to end up in the denominator, right? So it'll be 2x cubed minus 5x squared to the 4th. And then we'd say, hey, you can factor an x squared out of there, right? So up top, we got a negative 6x and 3x minus 5. But, keep in mind that x squared that's coming out, this whole thing is still being raised to the 4th power, right? So that's why I put this extra set of brackets right now to say I'm factoring an x squared out of this, bringing it out here, but it still has to be raised to the 4th power, right? So now we can raise it to the 4th power and pull it out of there, right? So what will that be? So we got negative 6x, 3x minus 5. And we've got, x to the 8th, 2x minus 5 to the 4th. Okay, but we got an x up top. So these guys are going to cancel. And there's our fully simplified form. Okay, so when you get an answer and it's like, well, that doesn't look like the answer in the book, it just might be that you're not quite all the way there yet, right? So you want to ask yourself, well, do I have an equivalent answer? Is there stuff that I could still do? Or, what did they do to get it in that form? What have I not done? Okay, so the next one. This. Copy that and paste it. I don't know. Hang on, let's see if I can. Apparently not. So I guess I can just write it out. Okay, so that's actually the derivative of that expression in D, right? D to the y equals, bracket 2x minus 3 times x cubed squared. That's what you're going to get as your expression for the derivative, right? Which we now want to simplify. So we're going to look through this and say, well, okay, do we have common factors or what's going on here? So what is going on here? Well, we get an x cubed and a 2, right? So we can get a 2x cubed times 2x minus 3, right? So that's this. And then in this set of brackets here, okay, what have we got? This is a 2x cubed. Well, okay, let's expand this out, I guess, right? So we've got 6x cubed minus 9x squared plus 2x cubed. Okay, so you can see how that's going to simplify, right? We've got a 6x cubed and a 2x cubed. So that's going to simplify. So we've got 2x cubed, 2x minus 3, and what's this? 8x cubed minus 9x squared. Okay, well, there's a common factor in these brackets, right, of x squared. So I can pull that out. We'll just move it up front. So that gives me 2x to the 5th. And then a 2x minus 3 and an 8x minus 9. Okay, and then that's it. Okay, so this is actually what's going to happen as a result of something, okay, of taking the derivative of that thing that's here, part D, and then this is the form you're going to get it into. And then the same thing happens in part E. Okay, but I'll give you a chance to copy that down if you wish. Okay, ready for E? So E, you can see, let's just write this out so it's kind of all on one page. So that's y prime. Or sorry, that's y. Y prime is so it's 3 times that, and then we've got 2x plus 3, 2x minus x squared 2 all over . So given y equals that, after you apply the chain rule, which you're going to remember, we're not sort of discovering it, but you can see that I get 3 times x squared over 2x plus 3 times, and then 2x plus 3 times 2x minus x squared times 2 all over 2x plus 3 quantity squared. And we now need to simplify this, right? So this can just stay for the time being. Oh, sorry, there's a squared on there, right? Yes. Okay, so we can actually square that. So we'll go 3x to the fourth over 2x plus 3 squared. So I'm not squaring that. I'm not squaring this denominator, right? I mean, I'm squaring it, but I'm not going to expand it. I am going to expand this numerator here because there will be terms that collect. Okay, so then we have our, so we got 4x squared plus 6x minus 2x squared all over 2x plus 3 squared. Okay, so that's 3x to the fourth. So here we've got 2x squared plus 6x over 2x plus 3 squared. And so, what do we got? Well, we have a common factor of 2x here, right? Here. So let's pull that out, combine it with this to give us 6x to the fifth. I've taken a 2x out of here. This will be x plus 3. And on the bottom, we're multiplying these two together. So it's 2x plus 3 to the power of 4. So we want to figure out if we can figure out a rule, which is called the chain rule, that allows us to determine the derivative of these complicated functions. So we'll go back to here and see if we can state your rule in words. So if you're looking at this one, so what did I do? Like, you know, here's the 4 and this and this, and then where'd that come from? So that's, you know, root x, that's a half x squared minus 5x plus 1 to the half, and we have a half x squared minus 5x plus 1 to the negative a half, and then where'd that come from? We got negative 3, negative 4, and where'd that come from? So what are we doing? So each of these have a power. First one is a power of 4. And we're really just doing what? 4 times 2x plus 3 cubed. Does that remind you of anything? What's dy by dA of a to the fourth? 4a cubed. Okay, so you're seeing 4 something cubed. Then where did the 2 come from? Okay, we got this half here, right? So we've got 1/2 this to the negative a half. So that seems like just, but where'd 2x minus 5 come from? Where did 6x squared minus 10x come from? The derivative of the, right? Okay, so what are we doing? We're taking the derivative of the power with respect to the base of the power. Okay, it's 4 times 2x plus 3 cubed, right? We are not changing the base of the power. And then we're multiplying it, though, by the derivative of the base with respect to x. Okay, these are a little more complicated here, right? Because you got powers and quotients. But, and then multiply by the derivative of the base with respect to x. Okay, so that's the chain rule, which we're now going to derive a little more differently, right? Instead of by inspection, and then we'll apply it a whole pile of times. Which take up most of the day, and I think your outline says that Monday is chain rule work pretty much, yeah. So, I mean, you probably want to do some on the weekend too, just to, yeah, you know. So chain rule. So we know how to determine the derivative of y equals x to the fifth and y equals root x. But how do we determine the derivative of something more complex, like 3x minus 4 to the fifth? Or square root of 3x squared minus 2x plus 1. We could expand 3x minus 4 to the fifth. Okay, you could, binomial, right? It'd be painful, but not that bad. And then take the derivative of each term, but that would take time. And it wouldn't help us with this, because we can't expand that, right? So, can't do that. In order to determine these derivatives, we need to develop the chain rule. So the function y equals 3x minus 4 to the fifth could be viewed as the composition of two functions. Y equals u to the fifth, and u equals 3x minus 4. Right? So we've got u to the fifth, where this is u. We can easily determine dy by du, right? 5x to the fourth, and du by dx, 3. But how do we determine dy by dx? Is there a connection between these three things? And if so, what is it? So let's first examine some simpler examples. So if y is equal to 3u, then what's dy by du? 3. If u is equal to 5x, what's du by dx? 5. Right. Derivative with respect to x of 5x. Yeah, so like the one above. Express y as a function of x. So y is equal to 3 times u, which is 3 times, but u is 5x, so that's 15x. And what's dy by dx for this? 15. So what's the relationship between dy by dx, dy by du, and du by dx? Well, this is equal to this times this, right? 15 is equal to 3 times 5. So dy by dx is equal to dy by du times du by dx. Now you can sort of remember that in the sense of this kind of, you know, it's not algebra and these aren't variables and they don't, you know, you can't cancel them, but you look at them and you can sort of say, hey, I could split that up, right? Right, as dy by du and du by dx, as if these things can. They don't. But, you know, to help you remember it, you can just sort of think, yeah, you know, put this on the bottom here and the top here, kind of. Why is this relationship true? Well, dy by du is the instantaneous rate of change of what with respect to what? It's the change of y with respect to u. So dy by du is how fast y is changing with respect to u. And we know dy by du, we worked it out, it's 3. So it means that what is changing what times as fast as what? So y is changing as fast as u. And du by dx is 5. This means that u is changing 5 times as fast as x. So if y is changing 3 times as fast as u, and u is changing 5 times as fast as x, then y is changing 3 times 5, or 15 times as fast as x. Or dy by dx, the rate of change of y with respect to x, is 15. Okay? So this is the chain rule. This is kind of it, and we're just sort of explaining that, hey, think of it as terms of rates of change. If y is equal to 4u squared, then dy by du is equal to? (8u). Du by dx is equal to, if u is equal to 3x plus 4, 3. Express y as a function of x in simplified form, right? Well, so we know that y is equal to 4u squared, which is 4, and u is 3x plus 4 squared. And that's what? 9x squared plus 24x plus 16, or 36x squared plus 96x plus 64. So that's y. So what's dy by dx? It's a derivative of that. This is easy. 72x 96. Calculate dy by du times du by dx. Okay, so dy by du, well, so let's just go here. That's 8u times 3, which is 24u. But it says express your answer in terms of x. So that's 24, and u is 3x plus 4. And that's equal to 72x plus 96. So is it true that dy by dx is dy by du times du by dx? Yes. Leaves us 3 pages. Okay, so here's the chain rule. If u is a differentiable function of x and y is a differentiable function of u, then y is a differentiable function of x, and dy by dx is equal to dy by du times du by dx. So if y is equal to u squared minus 3u plus 2, and u is equal to 2x squared minus 3x, then use the chain rule to determine. So this notation means dy by dx when x equals 3, right? Or y prime of 3 is what we would in prime notation, or f prime of 3 in that, right? So in other words, get the derivative and then work it out when x is equal to 3. All right, so what do we got? Dy by dx is equal to dy by du times du by dx. So dy by du is qu minus 3, right? And what's du by dx? Okay, that's 4x minus 3. Now we want to work out the derivative when x is equal to 3. Well, so when x equals 3, u is equal to 2 times 3 squared minus 3, which is, what? Sorry, 3x, so 3 times 3. So that's like 18 minus 9. So when x is equal to 3, we know that u is equal to 9, right? Just by definition. So we're going to go in there, in here, and we're going to put u is 9, and x is 3, and then work this out. So dy by dx when x is equal to 3 is equal to 2 times 9 minus 3 and 4 times 3 minus 3. Which is what? We got 18 minus 3 is 15. And 12, 9, there's 135. Okay, so dy by dx when x is equal to 3 is equal to 135. Okay, so we had a function y in terms of u, u in terms of x. We took the derivative with respect to y, dy by du, and du by dx. Since we had to work out at a specific value, we put that x value in, worked out the u value that corresponded, and away we go. If y is equal to 3x minus 4 to the fifth, then determine dy by dx. So if we let this be u, okay, so 3x minus 4, then what's y equal to in terms of u? So what's y equal to? U to the fifth, right? We're just saying, hey, that, right? Okay. So we're just going to say, let that inside fraction be u, or sorry, inside function be u, right? And then we just got y equals u to the fifth. Okay, well, dy by dx, we know, right, formula. So since we've written y with respect to u, or in terms of u, we do dy by du. We have x in terms of u, so du by dx. Dy by du is, what's the derivative with respect to u of y? What's this? 5u to the fourth. The derivative with respect to x of this is? Three. So dy by dx is 15u to the fourth. And so wait a sec, so dy by dx. So what's u? 3x minus 4 to the fourth. We'll do a couple more examples of this with the u stuff, and then we'll drop u and just go straight to the, basically the forms that you were looking at in when we first looked at it, right? Where you said, well, wait, it's just this, and okay. Well, trust me, it really is a lot easier, right? But we need to build up the basics in terms of this first. So, if y is equal to 3x squared minus 2x plus 1, then determine dy by du. What should we let u equal? So we'll let u be the inner function, right? So what's the outer function? The outer function is take the square root. Square root of what? The inner function, which is what? 3x squared, but we're just going to call it u. So we got y equals root u, right? So now y is equal to square root u, which is u to the half, right? I mean, if we want to actually do stuff. Dy by dx is dy by du times du by dx. Let's extend that. So what's dy by du? Because we've written y in terms of u, dy by du is? Yeah, so it's 1/2 u to the negative 1/2. And what's du by dx? Six x squared minus 2. What? Oh, right. So I said it's just 6x. I said, no, it's 6x minus 2. 6x minus 2. Right, gotcha. Okay, so what is this? Well, it is 1/2 times 6x minus 2. Oh, well, that's just 3x minus 1. Over the square root of u. Right? So the half times this. Now we're multiplying this times this times this. So a half just so happens that 2 is, right? So 3x minus 1. The u goes down. But we don't want u's in there, right? So what do? Becomes the square root of 3x squared minus 2x plus 1. So there's what we want. Tip 1 right down. There's nothing left. No, I don't know. They should come with like a replaceable tip or something. As long as it writes. We do not always have to make a substitution for u. The chain rule could be thought of taking the derivative of the outer function with respect to the inside function and then multiplying by the derivative of the inside function. It's illustrated in the example below. And this is basically the way you pretty much, just the way I do it. If I'm doing chain rule, I'm not replacing things with u's and writing all of that stuff, right? I'm just going to say, all right, this, and then this, and we're going to do 4 or 5 examples like this. So, dy by dx, express your abstract form. So you start off, it's going to be 7 times this to the power of 6 times the derivative of this. Okay? Now when you get real lazy, you just actually write the derivative of this, and you don't do that. But in the notes, we'll be very formal. We'll always write this. But in real life, and if you look in the answer book, I'm pretty sure they don't necessarily stick that step in. Okay, but that's 7 times 3x squared minus 2x plus 1 to the 6th times 6x minus 2. Do not expand the expression. Those of you that like to expand things, don't expand that. But a common factor of 2 here, right? So let's go 14. Let's lead with the simple. This will be the simple one, simple factor, right? So we'll start with numbers, then simple factors, and then more complex factors. Okay? So it's the outside function, which is something to the 7th, right? So it becomes 7 times something to the 6th, times the derivative of the inside function, which is now this. Okay, so we get 7 times this to the 6th, right? So just pretend that's whatever. Okay, times the derivative of the inside function, and then leave it in factored form. Okay, example 7. Nope, it's on this page. Differentiate and express your answer in factored form. So what's the very first step? What do we got to do first? Well, we got to write this as we got to get rid of the radical, right? So we got to change it to exponential form. Okay, so it's 3x squared minus 8x plus 2 to the power of 3 halves, right? Because the root is 2, but there's a cubed in there. So it becomes 3 halves. Okay, everybody good with that? Like, you're all good. Looking at it, you say, yeah, okay, I see where you got 3 halves from. Okay, so f prime of x. Okay, 3 halves. Whatever's in the brackets. To the 1 half. Okay, normal stuff, right? Every day, if I said x to the 3 halves, you said 3 halves, x to the 1 half. Okay, so 3 halves expression to the 1 half times the derivative of the expression that is inside, the inner function. Okay. I generally I would just write 6x minus 8, but for you to, Okay, so well, what? We get a 2 out of the 6x minus 8, right? Pull that 2 out, multiply it by 3 halves. I'm just left with the 3. I pulled a 2 out of this, so I've got 3x minus 4. And I've got the square root of this. Okay, so 2 came out of here. Multiplied 3 halves, became 3. This just moves up in the ranking order, right? I like to stick it first. So here's more statement of the chain rule, right? If y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x, then y equals f of u, which is f of g of x, is the differentiable function, and dy by dx is dy by du times du by dx, or the derivative of f of g of x is f prime of u times g prime of x, which is f prime of g of x times, so it's, take the derivative of the inside function, or sorry, derivative of the outside function times the derivative of the inside function. Okay, I say it's easier to do than it is to say, right? You just, okay, so who went and multiplied two things together, right? Now we got to do the product rule, right? So we've got two things being, and the chain rule. Yeah. Because the two things are being multiplied together happen to have powers and expressions, right? Okay, so we have to apply the product rule and the chain rule. And is now the front, right? So use product rule and chain rule. So product rule first. So g prime of t. Okay, so the product rule says I take the first function, so t squared plus 1 cubed times the derivative of the second function. Change that to a 2. Plus the second function times the derivative of the first function. Okay, so that's just product rule, right? F times g is f g prime plus g f prime, right? So that's product rule. We haven't done chain rule yet. Now in order to do these derivatives, this one here and this one here, we're going to have to use the chain rule now. Okay, so we've got our product rule down. Okay, equals, okay, so we got the t squared plus 1 cubed. Okay, so the derivative of this is what? Well, it's 4 times 3t minus 2 cubed times what? Okay, so outer function is 4 times 3t minus 2 cubed, and then the derivative of the inner function is 3. Okay, so this is the derivative of the outer function, and this is the derivative of the inner function. Plus 3t minus 2 to the 4th times a bracket. Okay, so we've got 3 times t squared plus 1 squared times what? 2t. Okay, what do we do with the quotient rule? It's so much more fun. So with the product rule, you just look at it and say, I have a product. Let's just set up the product rule, right? So it's like fg prime plus gf prime. Now, I'm going to go and actually do the derivative of this, but oh wait, I got to use the chain rule. So it's 4 times 3t minus 2 cubed times 3, the derivative of this. And here it's 3 times t squared t squared plus 1 squared times the derivative of the inner function, which is 2t. Okay, so now we just get to simplify this, right? So we can see there's going to be some common factors, there's numbers and all of that. Let's clean it up a bit first. So 4 times 3 is 12. T squared plus 1 cubed and 3t minus 2 cubed. Okay, so that's just the first set. That's the first expression before the plus sign, right? Plus, okay, and again, let's clean this up. So 3 times 2t is 6t. And let's put stuff in the same order. So now we'll do the t squared plus 1 factor, right? So t squared plus 1 squared, and then 3t minus 2 to the 4th. Okay, so now we can pull common, right? So what's the number? So 6, right? 6 goes into 12 and 6. T, not common. T squared plus 1, what power? Squared, right? The lower one. And 3t minus 2, cubed. Okay, so our common factor is 6 t squared plus 1 squared 3t minus 2 cubed. Okay, that's our greatest common factor. We're now going to have two terms in the plus sign. We got to have something for this. So to get the 12, I need a 2. I'm short a t squared plus 1, so I got a t squared plus 1. Okay, and I've got as many of these as I need, right? Cubed. To get a 6t, I'm going to need a t. I have all of these I need, because these match, they're squared. And I'm short a 3t minus 2. So now all we got to do really is just expand that last set of brackets, right? And collect like terms. And we got a couple more lines. Will it take 2 more lines? Can we do? Let's do it in 2. Okay. So equals 6. So 2t squared plus 2 plus 3t squared minus 6 minus 2t. Minus 2t. And we're one step away from our final answer. We just have a couple of like terms to collect here. 6 t squared plus 1 squared 3t minus 2 cubed 5t squared minus 2t plus 2. That's our final answer. That's what makes marking Math 31 just so much fun. You know, if you make a mistake somewhere. All right, so here, I'll leave that up there for a second. Just look through. In a sense, it's kind of fun. I mean, it's just like solving a little puzzle or whatever. It's fun. Where'd it go?
I love combinatorics. It's like colors. I like
Just sitting down in class. You were being sarcastic.
He's like, what? Seriously?
Some people, the combinatorics is kind of neat, but it's always tough to get the same answer as everybody else. Okay, so let's change it to exponential form. It's a product. Got to use the product rule, right? So it's x squared times d by dx of 1 minus x squared to the half plus 1 minus x squared to the half times d by dx of x squared. So at least this one's not bad, right? I mean, that's just 2x. So this, not so bad, that's just a 2x. This, need to use chain rule. Okay, so we got x squared times 1/2, 1 minus x squared to the negative 1/2, right? So that's the derivative of the outer function, right? A half times this, 1 minus x squared to the negative 1/2, times the derivative of the inner function, which is negative 2x. Okay, so that's this, plus 1 minus x squared to the half times the derivative of x squared, which is 2x, luckily, right? Hey, wow. Okay, so let's kind of simplify what we can here, right? So I'll get like 1/2 x squared and negative 2x would give me negative 1x cubed, right? So negative x cubed. And we'll leave the 1 minus x squared to the negative 1/2, right? Plus, and again, let's start with the simple factor, which is 2x. And we got 1 minus x squared to the half. So we can factor out, well, we get rid of an x, and we can get rid of a, what are we doing here? What's the factor for these two? 1 minus x squared to the negative 1/2, right? Okay, so let's factor out a negative x and a 1 minus x squared to the negative 1/2. So now we need to rebuild this term, which is missing an x squared, right? Because I need an x cubed, I've got an x out front. So this is the common factor. Multiply it by this, we're going to get back the first term, right? That's what has to happen. You multiply this by this, you get this. You multiply this by something, okay, what do we need? Oh, well, it's going to have to be a minus because we need a plus 2. So minus 2, and what power of this do we need? Okay, it'll just be 1 minus x squared to the 1, right? Okay. You multiply a negative 1/2 by 1, you're adding the exponents, you get positive 1/2. Okay. Multiply negative x times negative 2, you get positive 2x. Okay, so we can expand this. So our common factor is our common factor. We get x squared minus 2 plus 2x squared. So let's go with negative x. Let's throw this factor in next. And go with 3x squared minus 2. And since that's negative, it goes in the denominator. And it gets turned into a radical. Okay, so negative 1/2. You have to go down below. It becomes positive 1/2. Don't bother writing it in the exponential form. Just change it to radical form. We get root 1 minus x squared. That is the answer. Ooh, only 2 more to do. Oh, look, quotient.
Can you hold for just like 1 second? Here, I have an edit now.
Okay, these will all be posted, right? So I mean, you don't have to. Okay. Okay, there's the easy part, right? The derivative of the outer function. 4 times whatever happens to be in the brackets, cubed. And just to be nice and formal, then we go times the derivative of the inner function, right? So it's the derivative of the outer function, 4 times whatever happens to be in the brackets, cubed, times the derivative of the inner function, which is 3x minus 1, x squared plus 3. That's a quotient. You can be doing quotient. So, okay, let's call this 4 over 1, 3x minus 1 over x squared plus 3 cubed, times, okay, so it's g, right, it's the denominator, x squared plus 3, times the derivative of the numerator, 3, minus the numerator, 3x minus 1, times the derivative of the denominator, 2x, all over the denominator squared. Okay. You will never expand a denominator. Numerators, yeah, you expand and you collect and all that. You will never expand a denominator. Okay, so chain rule, 4 times inner function cubed times the derivative of the inner function with respect to x. That happens to be a quotient, so quotient rule, g f prime minus f g prime over g squared. Okay, this can be collected and simplified, right? So we're going to do that now. Actually, you know what, here, we'll split this out. We'll go. Thing is, we got something going on here with x squared plus 3, right? So let's split this out into its denominator. Instead of saying the whole thing cubed, let's write this as a cube because it's going to multiply this, right? And they're the same. Okay. What do we got? 3x squared plus 9 minus 6x squared plus 2x over x squared plus 3 cubed Okay, so we got 4 times 3x minus 1 cubed.
How did you
Yeah.
Why is it cubed on the bottom?
It's not. It's good. It's amazing. It's like afternoon, Friday afternoon, and you're still awake. So negative 3x squared plus 2x plus 9 over, and now we can multiply these two guys together and get the power of 5. Or maybe you see that, or maybe you see this. So we're taking the negative out, so we're going to have a positive x squared here, right? Positive leading term. So negative 4, 3x minus 1 cubed, and then all of these something the same. Oh, yeah, well, okay. If h is a differentiable function, then determine the derivative of each of the following. So it's going to be 3h. So it's 3 h of x squared times h prime of x, right? And we can't do anything with that. And this one's going to be h prime of x cubed times 3x squared. Right? So the derivative of the outer function, we don't particularly know, it doesn't have a power on it or anything, right? So it's the derivative of the outer function times the derivative of the inner. And in the first one, we knew what the outer was. It was something being squared. We didn't know what the inner was. Example 12.
Oh, this one's tough. Tough.
Yeah. So let's see if we can get this done. So first, we rewrite it in exponential form, right? And then expand the page like 6 times because we know. Okay, so how does it start out? Well, it's a half times whatever's in the brackets to the negative 1/2. Right, that's the derivative of the outer function times, let's be formal about this, times the derivative of the inner function Okay, so now let's do the derivative of the inner function. So we've got the half, and then we've got the x plus Okay, so what do we got? Well, that x sitting there, the derivative of x is 1, plus 1/2 x squared plus 1 to the negative 1/2 times the derivative of the inner. So I'm doing chain rule on this little bit in here, right? So it's a half x squared plus 1 to the negative 1/2 times 2x. Okay, so let's just take this thing. And what do we got here? Okay, so the 2, so we've got an x. Okay, so that 2 took out the 2x. What's this x? There. So nothing much is going to happen with this. Okay, that's a negative 1/2, so that comes down here. We need a common denominator. We're just gonna, it's this times this, right? Plus this over the whole thing. So I'm just gonna write it out. And then we just combine it all into one because it's multiplied. So it's root x squared plus 1 plus x over 2 root x squared plus 1. Phew, finished. Done. Just copy that out. Then if the bell goes, you can just leave in peace. No worries. I wrote it all down, but. So I gotta do this practice. You might want to do a little bit on the weekend, and then I think Monday is work period on chain rule as well. But don't save it all up for one 80-minute period of class.